Labs next. Welcome everybody to Inquiry Labs next Open Academy. Today we are going to have a very interesting presentation from Wilson and Tobias. Both of them are coming from PKNOA, and we are going to hear about an actor modeling based database backend and how it was designed and developed at their company. Okay, guys, the floor is yours.
Thank you. First, yeah, thank you for the invitation.
That was Tobias talking. My name is Wilson Edgar, and we also here with our project manager, João Tacanho. I'm sure you guys will have no problems in pronouncing his name. It's a pleasure to be talking with you guys, and I really hope you guys enjoy the talk and the technology that we've been working on for the past not just month but years. Okay. All right.
Okay.
You have to.
Do you still see us?
Yes.
Okay.
Can you still see the screen? The share screen?
Yes.
Okay, fine,
fantastic.
Okay, thanks. So just quickly the agenda. First, we will very briefly introduce what PKNOA is, and in this context, I will also explain why we have chosen the topics that we will present today. These are three aspects of PKNOA. First, the actor modeling, then complex event processing, and then the last point we will look at is laziness, and this is a very good topic for Friday. So PKNOA is a data management system, I would say, that is directed towards machine learning, data mining, and things like that for really big data. And it has several components. The first component is the actor modeling. This is the modeling that is the data model behind the database. Then storage, a distribution framework. There is some feedback. Is it my fault?
Sorry, there is some problem with the screen there.
Hello? We can barely hear you. It's very
far away.
Yeah.
far away, and there's a bit of feedback. Hello?
Yeah, we are here.
Okay. Can you still see the screen?
No. So
No.
Something is not working with the sound.
Now we see.
So it's very strange because we can see it in Hangouts, but it doesn't seem to work in YouTube. So, now it's okay. Okay, now it's working.
Okay. Should we make the page up over here?
Yeah. No, the problem is you're now not in play mode, so I have really to scroll. That is why I wanted to go into play mode.
Let's let me put again the play.
It's not on.
Still, we'll see the slides?
Yes.
Okay.
So the components, the actor modeling, that is the data model we use. Then we have a storage engine, of course, which is tailored to this actor modeling or this data model. Then we have a distribution framework, complex event processing framework. Then we have a layer of operators, which is actually a kind of query language. Then we have APIs and generic API and more specific APIs for machine learning. And finally, the machine learning data mining framework. We will talk today. These are a lot of things, and we cannot talk about everything. So we thought of what could be interesting for today, and we shows the actor modeling, then the complex event processing, related to this bit about the API, the generic client API, because we think that you are coming from a modeling world, so I guess that you are interested in our data model. We know that you are working on complex event processing, so we chose this aspect. And finally, we will talk about a challenge. This is the laziness, the lazy execution, and we hope to get your feedback there. In general, so the slides are not very dense. Most things that are interesting I will say, and I appreciate when you have a question or a doubt, please interrupt me and ask directly. I think that's easier when we have a dialogue immediate instead of postponing all the questions to the end, okay? Hello?
Hello? They're gone.
They're gone. Hello?
We are here, yeah, it's okay.
Okay. So, actor modeling. We start with looking at the traditional data model for storing data, that is relational databases. And the relational data model is generic. So, in principle, we can store any kind of data in a relational database. And of course, that is good. But there are some weak points that led us to an alternative, which is the actor modeling. The first thing is what is often called object relational impedance, and this means that we store our data in tables that have certain relations between them. On the other hand, we are working in programming environments that are usually object-oriented, or perhaps there are other patterns. Sometimes they're functional or merely procedural, but basically we have objects that we manipulate in memory. And when we try to store from this viewpoint to the relational model, then we have to restructure all the data, and sometimes it is quite annoying because it's not a one-to-one relation. There's even a whole market about this with business object layers and so on that do this kind of things for you.
Yeah, just to continue. I mean, the object relational impedance is actually one of the great causes of software, not only for inserting bugs, but also for software taking so long to develop. In most business worlds, I mean, the object-oriented programming won. I mean, the most used language today is probably Java, followed by C#, and they're languages that like really favor the object-oriented approach. With the object relational impedance, what it means is that the programmer spends most of his time trying to convert from what is in the relational database by writing multiple queries, and then to convert it to objects. And that conversion usually is what is very time-consuming, and it never actually works out really well. As Tobias was saying, I mean, there's a whole parallel market that builds stuff around it, and then also for the market itself, it makes it quite difficult because, for instance, if you start a job and you have to learn about Hibernate, but on your next job you have to learn about the entity framework of Microsoft, these are two very different tools, and it requires the programmer to constantly be learning about these new tools and constantly be fighting the same fight. And that's one of the problems that actually led us into creating PKNOA, is that this constant refactoring of both our model and the database itself.
Okay, thank you. The next point here is managing change or reflecting change in the data model. Usually in a relational database, all the data is static, and you can change. You can change it. You make an update on this data. This is fine. There's no problem as such with this, but you lose the previous state. So you are always looking at a snapshot, and sometimes you lose information by this. So
sorry,
yes.
Let me just stop you right there. I guess you are not on the "you shouldn't have to wait" slide, right?
You don't have to wait.
So the problem is that I think that the screen share is either stopped or I don't know, because we are still seeing the slide with the guy sitting in a chair.
With the guy sitting in a chair, you don't see the guy standing in front of a wall?
No.
No.
So the problem is, I guess, is that you are sharing your slides, but not the presentation. So we only see the update when you go back to the slides.
Yeah. Yeah, I think I will just scroll down, right?
Yeah, just scroll here and okay.
It doesn't work either. How do we do this?
Maybe you have to have.
Yes.
It's just save like that. You can. And then. Like this.
Okay. Yeah. But we have to. You see the slide, the guy in front of the wall?
Yes.
Okay. So I was talking the second point, reflecting change. And usually reflecting change, but what people do to solve it, they add another layer. So, like for example, a history, where the change over time is recorded. But this is an additional database within your data model, right? So, and the final point is speed. So there's a lot of discussion recently in the big data world about the performance of relational databases, NoSQL databases, and what is all out there nowadays. But in principle, the problem of relational databases is that they're very heavy. There's a lot of metadata you need for the relational database. You have transactions. You have a lot of things that make simply accessing data slow compared to just getting the data off the disk. And yeah, this is a problem. And one of the things we want to tackle with the actor model, with the actor modeling, and with the storage engine built on top of it, is speed. So, what is actor modeling anyway? Actor modeling as such is nothing revolutionary new. It is, in fact, well known. It is very, very similar to object-oriented approaches that are around for a lot of years, of course. So let's talk about terminology. So we have entities that we call role, actor, and messages. Role is more or less what you would say is a class in the object-oriented world. An actor is an object, so it is an instance of a class or of a role, you could say. Then the member variables, so the attributes in the object-oriented world, we call properties. Properties are defined by roles, and actors actually have properties. For example, a name. And then actors exchange messages. This is, I don't know, perhaps you are familiar with Smalltalk, and in Smalltalk, the term message is used to refer what in other languages is a method. So this is really very close to object-oriented designs. So the difference, an important difference that comes with PKNOA is that message have structure. So we define what a message can be. They follow a grammar, and we store in our storage engine. We store data as instances of messages. We call this entries. So these are instances of messages that are exchanged, and we store them with a reference to time.
We initially started with the actor modeling, and the reason why we chose it is because it's easier to represent data. Well, it's easier, at least for the human brain, to understand the data represented as a conversation between actors, as opposed to as tables and columns. The reason why we did this, and the reason why we chose this message infrastructure, is because it's easier for us to understand in terms of what person A is saying to person B, as opposed to what's the inner join that I have to do between column A and B. What we've changed from the existing structure, like Tobias was saying, is that our messages, they're not free messages. The actors cannot talk amongst themselves freely. They have to follow a vocabulary. They have to have a grammar, because otherwise there would not be a language. Just like we humans need a grammar, we need a language to be able to communicate. Our actors also follow a very strict grammar. Within that grammar there are semantics, but they have to follow the grammar in order for them to communicate amongst themselves. What do we do then is that each message is then quantified and stored with a time reference, again, just like Tobias said. To complete what he previously explained about the roles, one thing that we try to do with the roles, the examples is as follows. You have an actor. Imagine that I am an actor, but in my life, I have multiple roles. At home, I'm a husband and a father. At work, I'm a developer and I'm the CTO. With my friends, I am the grumpy one. I am the same person, but depending where I am, depending on the context where I'm inserted, I might have different roles, or I might assume different roles. And because I'm assuming different roles, for each role, my properties are accentuated, you know? Different properties are accentuated when I am at a given role. Are you guys, does this make sense so far? Do you guys have any questions?
Yeah, it makes sense. No questions at this moment.
Okay. Then.
One small question about this time reference. That is it logic time? So somehow you use some logic time, I would say, or is it real time? So let's say
it's real time. Yes.
It's measured in UTC. With the granularity.
What is the granularity of this time stamp? Seconds, milliseconds, or how precise is this?
It's 100 nanoseconds. That's the base unit.
100 nanoseconds. Okay.
Yes.
And even in a distributed environment, you are able to have this precision?
I don't say that everything that happens in the works, every 100 nanoseconds is stored. That's the granularity.
Oh, okay, I see.
The user application can use. But of course, for example, when you send data through the internet, that already takes longer than 100 nanoseconds. So it is.
My question would be about, so do you use some time synchronization and something like that between the different nodes if you have a distributed environment, or?
No. This time we have another notion of time for the system. This time is a time that is associated with the data. For example, a very typical example. Let's say the actor is a sensor, and the sensor sends data, and then the date refers to the
collection date.
Yeah, the time.
Okay, so when the information, let's say, appeared or saved. Okay.
For example, the temperature at noon.
Okay.
That's a good example. You could acquire the temperature data at noon, but just send it at 1 o'clock in the afternoon.
For example,
You
and
know?
these are two different things. One is the application domain that time, and the other is when we internally created the data record. But that is something totally different.
Okay. Okay. Thanks.
So when we talk about time in this sense, this is really something that is defined by the user application. And the granularity of the user application, in most cases, it is of course not at a microsecond level. It is usually per second or per minute or something. But from what we provide, we can go down to 100 nanoseconds. Does that make sense?
Yes. Yes.
Okay. Right. So the next thing, the actor modeling is something that goes from the storage engine to the user application. So we, for example, in a distributed system, we communicate data records in terms of actors, messages, and message instances. Now, for the application side, we have an API that we call Themarima. Themarima, the term comes from linguistics, so it's not really a term that comes from computer science. And a thema is something in linguistics you are talking about. It's a topic. And rima is what you say about it in concrete, the comment.
Right. So basically, what we're saying is that imagine that you have a sensor sending data to the server. Now, the sensor, theoretically speaking, as long as it follows the grammar, the sensor could actually say anything to the server. But to restrict what the sensor is saying, to actually give a certain sense of rule to the system, we restrict the sensor in saying you can only talk about these topics. Okay, so you can only send data of temperature, and you can only send data of
wind speed.
Exactly. So we restrict the kinds of conversation that the actors can have. So it's sort of like being a benevolent dictator. And in our system, actually, there is no freedom of speech. You can talk about a lot of things, but all the speech is actually controlled. The Themarima, what it does give us is that it gives us order in the system. It's our way to give the end programmer a way to create order. Otherwise, it could become chaotic in the sense of if the actors can say anything to one another, then it would be very difficult to track that information.
Yeah, perhaps to go a bit deeper in this example of the sensors sending the temperature. Very typical, what we mean with grammar here would be the definition of that. For example, in the sense of the International System of Measurements, we say this is temperature, and this is the unit. This could be the definition of a message, and then a message instance would say, for example, 20, but you don't know what 20 means without knowing what the message is. So the message tells you this is temperature and this is degrees Celsius. Okay, then in the application and in the application view, the actor is an interface. I think that's the correct term, right? An interface. So an abstract class that you have to define for your concrete application. And what actors are in general is defined in the interface, and what actor is in concrete for your application, for example, a sensor that is defined by your code in terms of just implementing this interface. This API is linked to the storage engine. And whenever you instantiate an actor, the properties are loaded from the database. So it's really something that is under the hood, and you just do object-oriented programming, and what happens to data is done in the background. Okay.
Okay.
So we go to the next topic. Complex event processing. So typically, PKNOA system is distributed, and each node has a single entry point, and we call it Bob, the builder. That's the picture. Internally, all these elements, all our components have nicknames, and this nickname is Bob the builder. So on the application level, when you define your system, you can define rules that Bob would execute. And rules are typically, there's a bit more about rules, but basically it's a condition and a consequence, like an if-then. So this is, and I think you do very similar things in your complex event processing environment, right?
Yes.
So rules are either triggered, for example, when data arrives, or scheduled, so you can run a rule once per hour, or they are custom. And custom basically means they are called from other rules. So the consequence could be to execute another rule. They have unique names, unique within the system, so you can call rules remotely. So node A can call a rule on node B, and node B then calls a rule on node E, and so on. From this, we get a directed graph of principal arbitrary complexity. And the engine that executes the rules is .NET. So there you can define your rules typically in C#, but basically you can use a BASIC or F#, whatever runs on .NET. It is with the approach of using such an execution environment, we protect our system, so its rules run in the sandbox, and it is free to the user to restrict numbers of files, numbers of threads, execution time, and so on and so on.
With the rules, what we wanted to create initially is that we wanted to create a very clean and simple interface. This is why we have the if and the consequence of that predicate. With this simple interface, which is very easy to understand and very easy to explain, we can then build on very complex systems because of what Tobias just explained. If a rule can call another rule, then not only the rule itself becomes a specialized node, but by calling another rule, you can then pass on the work to someone else, but thus creating this directed graph. But when you create this directed graph, it means that you can also create loops, and you can make actually very complex processing, and you can make it on a distributed manner. And you can make it by implementing actually very, very simple rules. I mean, it's just a thinking of, if you think about an algorithm, that's exactly what we do. We break down the problem into smaller functions, and then the functions call each other until, you know, we get the desired result. We just did this in a way that is slightly bigger. You have classes that implement very simple interface, and these classes can call other classes. Now, with this very simple interface, you can actually create very, very complex computations, but they're very easy to break down in the end, because you can always go down to the root. You can always know what's missing and what's not missing. The other thing that we've did with our complex event processing is, although PKNOA is a distributed system, each node has a specialized complex event processor. What does this mean? And this is why we were explaining a bit ago that a rule can call another rule on a different machine. Now, the point of the rules being specialized is that you can actually, on a distributed system, you can have designated nodes to do designated types of work. Now, for instance, imagine that you have a node with a GPU in it, and you want to do some sort of, filter, do all the filter on all the data training for machine learning algorithms. But mainly, you want to do that on that machine, on that node, because it has GPU, and you'll get more for your buck. So this is why we've made them specialized, because this way you can choose where the computation is going to run. The way we query data, that's distributed, but the way that we then analyze data is specialized.
Yeah, and one thing, perhaps I'll first talk about use cases before going into more details. So obviously the simplest use case is an insert trigger for data validation, and you check the data, and when the data is okay, you insert. Otherwise, you reject. Another use case that is important for us in the context of machine learning is restructuring and pre-computing, restructuring data into pre-computing, for example, statistics. Restructuring of data, typically we create vectors, matrices, depending on what we want to do with the data. And then the third point, but where Wilson already was going into is distribution of computation. So typically, we don't want to bring all the data in a big data system to the computer where the client application is happens to run, but we want to bring the computation to the data because there are a lot of data. Therefore, we specialize the different nodes using rules, and then running algorithms where nodes have different roles. So it goes beyond just MapReduce. We can do MapReduce, but everyone can do MapReduce basically. And here we can specialize nodes so that one node, for example, sorts its data locally, and the other node merges two streams of sorted data. Or we can cluster. One node holds the clusters, the other nodes are sending the pivos. Okay.
Okay.
Yeah.
Questions? So then we come to the last topic, which is more the future work and challenges side, and that is laziness. Laziness concept that is very well known in functional programming, and it has two sides. First is you only compute or perform computations when the data, when the result is really needed. The other side is that once it was computed, you only recompute it when the data has changed. So delay the execution of computation and reuse the results if possible.
This is a very important concept in the world of big data, because dealing with petabytes of data, you don't have enough memory to load them and to do whatever kind of computation that you need. So in order to better use the resources, we actually have to use lazy computation. That's the importance of lazy computation, is that once you actually have, I'm not even going to go into petabytes of data, just gigabytes of data is already enough to cause you a few problems. I mean, not everybody has machines that with 128 gigabytes of data. So basically, what we're trying to achieve with this is that you can still have hundreds and hundreds and hundreds of gigabytes, if not petabytes of data, and you can still run your computations not only on a timely fashion, but with the available resources. You don't need to have a supercomputer to do it, because we will use the available resources lazily, but we will use them to then evaluate the result.
Yeah. And what we do in concrete is we retrieve data only when they are really needed on the other nodes. Otherwise, we do the computation there on that node. The next is that we to send data only when it is really required. So from the user side, from the application side, you would have the view that one data point is retrieved from the database in the moment you are doing something with it. Internally, of course, we use buffers and so on and so on. But on the level when you look at buffers, there's only buffer sent when the old one is exhausted and the user application requests the next data point. Then what we also do is we store computation results, and this is mainly about statistics, from simple statistic, but like average and median and so on, but up to regression analysis, for example, that we compute regularly and store in the database. Finally, what we do is we maintain data in memory, previous results, for example. But with this, with the last 2 points, there are some challenges. So the first two things, or the first 3 things we already do. The last thing is still ongoing work. But even with the things before, there are some challenges. And I think there are challenges that you know very well from the slides I saw from you, Akos. The first is we have to identify the need for a recomputation. For example, recomputation is necessary when new data is available. Probably necessary, not in all cases. Then previous may differ from previous ones in very subtle aspects, like, for example, a different scale. I mean, we have computed the statistics hourly, but now there's a query asking for the data per minute or something like that. And then I think even more tricky, more difficult is to understand that queries are equivalent. They may be worded differently, but they are concerning the result, they are equivalent. And that is not always easy to understand. And then there's another set of challenges, and that is what we have to look into is what is the best heuristics, the best trade-off. For example, we are relying heavily on what the operating system do. Operating systems today cache a lot of data. They cache entire data files and so on and so on. And we have to trade off our caches, our PKNOA caches, with concrete query results against the generic OS cache where data files in memory. Then, of course, we have the trade-off memory against time. So sometimes it's good to have things in memory, and then the execution time is very fast. But sometimes it's not really worth. You have you pollute your whole memory for winning at the end 10 milliseconds or so, and that's really not worth. And here we have to learn how to do the trade-off. And finally, pre-computation against on-demand. And whenever we can speed up frequent queries by pre-computing it's worth doing. But we don't want to waste time pre-computing data that are never used.
So those are the challenges that we are facing right now. I mean, for the last point, for the pre-computation, what we basically store nowadays is mainly statistics that we're working on. But even then, I think it's equivalent to having a garbage collector, a programming language, a garbage collector, because it actually stops the computation, it stops everything to do that computation. And that can be expensive. So yes, in the end of the day, it's a trade-off that we're still trying to find the most balanced point.
and of course, we hope for answers from your side. And that ends our talk. Thank you very much for your attention.
Okay, thanks a lot for your presentation, and I think we might have some questions to ask the audience here. Do we have some questions? First, applause for the presentation. Nice. And then, please, if you have something in your mind, then feel free to ask, because I think this was a really high-level overview on your system, and there are a lot of tricks and tips in under the hood, so I suppose there might be some questions. On my side, I think, or I might not get it correctly, but you were talking about querying and queries, and to be honest, it was not completely clear for me that how you define your complex event processing system that it can execute on the different nodes, and it is able to call other rules. Are they also true for the querying capabilities? So when I'm only reading the data, and I would like to get some filtering or whatsoever from other nodes, will I be able to define these queries using the same concept as for these complex event processing rules, or is it something completely else?
No, that's one of the points of actually having the complex event processing. Now imagine that you've defined a filter. As long as the filter follows that interface of the interface that we've defined, all the rules will have a name. So what we do under the hood is that once you call the name and the name of that rule is unique, being unique, we can find it anywhere in our cluster. Once we find it, we execute that computation and give you back whatever result you asked for. So we actually just build the machinery to call on different nodes and to make communication seamless to the user. But that's the actual point of the complex event processor, is that you can give it names and then you can then call it as opposed to executing a query. I think it's very keen of being a stored procedure in the relational database.
Okay. We should briefly explain that we have a distribution framework anyway, independently of the complex event processing.
Oh, yes.
That is, and we use sharing and we use replication. So you can define that you want to replicate this database on another node, and then that is for data safety, the backup. Yeah. The other is sharing, where according to a balancing algorithm, data is distributed in the system. So when you do a query and you know that the data is distributed, then this part that the data is collected from all the nodes, that is done anyway. That is one component. I think it's PEX, the Postman, that gets all the data from the different nodes. On top of this, you can build specialized algorithms. I think a very typical problem, or a very problem that is easy to understand is sorting. I don't think that sorting is exactly a MapReduce, but it is similar. But you can optimize your system by specializing the nodes that merge streams and then send it to the next level and so on. And that you would typically do with complex event processing. You would one node would assign the task of merging by calling a function on the other, a rule on the other node. And when you want to get the data, that calls a rule on the first node, like a callback. Does it clarify your question?
To be honest, it just made me a little bit more confused, because when I don't get at this point, then sometimes you might be required to send complete databases as messages between nodes, or how can we think about this when you mention this sorting? you mentioned that you might send out, let's say, a part of a sorted list to another node, and then it will be able to merge it with another part of the complete array or whatever we are sorting right now, and then the output of this particular node will be the merged parts. These two parts merged together, and then it will be, you know, another one, and so on. So it might happen that the one message may contain quite huge amount of data.
Yeah, we are always talking, in this case, we are always talking about streams.
Okay.
So what the nodes see is that data arrive, the nodes do queries. They query the local database, and then they query the database of their neighbor. And then they merge the stream and send it to the next stream, to the next node. Sorry. But this is just an example to illustrate what can be done with the complex event processing.
And okay.
And the role of the complex event processing here is to give the specialization. Let's say you have 128 nodes or something like that. Then all of the nodes, and you want to sort all the data. Then first, on the first level, all nodes do the same. They sort their own data, right? And then half of the, for example, this I don't say that the best sorting algorithm in the world, but it could be made like this. Then half of the nodes receive the streams of themselves, and the other half of the nodes and merge them, right? And then we have a distributed merge sort.
Yes, but then at one point of time, one node will need to contain all the data, and this might not fit into its memory or something like that. So,
Yeah,
but when one data sends all its database information to another one, it might not fit into the memory. So that's the point when I don't see how this.
We don't fit it into memory. That's the use of a stream and the lazy evaluation. Is that you don't have to fit it into memory. You can be sorting petabytes of data on a machine with 1 GB of RAM, but because the data is being treated as a stream, you will only have in memory whatever you're computing right now. So the memory footprint for that is actually quite small.
Therefore, the example of merging. In merging, you can always decide the next one to go.
Okay. So most of the rules are those which fits well with this. Okay, with streaming-based data, stream-based data.
Yeah, perhaps this is something we should have mentioned at the beginning. That the storage engine that is just data. How do you say in rest, right? This data that is on the disk. But whatever we do in the distributed system, these are streams, and this is data in motion always.
Okay.
If you want, of course, you can define a rule that gets data from another node and stores it. But I mean, that's what the rules are made for. You can customize them to your problem.
Okay. For me, it made things clearer, I would say. Okay. Thanks. So.
Okay, so we have a question from one of our colleagues. Many existing complex event processing solutions use event condition action style of rules, where conditions may refer to certain contextual data. Is this also the case for PKNOA?
Yes, it is the case of PKNOA. The rule always knows the context that is running. So if the rule actually needs some data for itself, it's the rule's job to load it, give it context, and and then do the processing. That's quite the case in PKNOA.
Yes, but perhaps the thing that I did not mention, there are two types of rules: stateless and stateful. The stateless rule is just looks at the input and does something. The stateful can maintain state. For example, when you just an example. I hope I don't confuse you with my bad chosen examples. So, for example, when you compute the average, in a rule, then you of course need the number of things you have already received and the previous average, right? And that would be the state.
Mm-hmm. Okay.
But you can also you can build a database in a rule if you want.
And that's why you are saying that, for example, this average would be just a snapshot, because you don't know if on the streams you have received all the data what you are storing in your cluster, right?
Yeah, you can, for example, average is simple because average can be computed locally and then maybe reduced to the overall average, right?
Mm-hmm.
And so you can, I mean, you can use a background job, a scheduled rule that does this once per hour or so, but you can also have a trigger rule that whenever data is inserted, you recompute the average. But in that case, you need state. You need to know the previous average.
Okay. Okay. See. Good. Can you say a few words about, let's say, some performance characteristics? You know, let's say, how many nodes do you handle, or what is your largest currently running instance of PKNOA?
Well, theoretically speaking, the number of nodes should be infinite. But we're actually getting into the benchmarks. We're actually like sending it to a number of nodes. We haven't had the official number of nodes that we can run, but our educated guess is that, you know, anywhere until 128 nodes we should run fairly easily. Above that, the rules that we have in place maintain, and this is why I'm saying that theoretically speaking, the number of nodes is actually infinite, but you know, there are technological limitations that I'm sure we'll run into as soon as we start having you know, an extraordinary number of nodes, like let's say 256 or 512.
Okay.
But in terms of performance itself, when we created PKNOA, and because we know exactly how the data should look like, we've created very efficient data structures. So PKNOA in itself is actually quite fast. We did some testing, I mean, not very scientific or not very in depth, let's put it this way. They're mostly trial and error and very superficial. But on a regular database, on a SQL server from Microsoft, you can do up to 140 write operations per second, or in MongoDB, we can go up to a few thousand operations per second. In PKNOA, we can actually do millions of write operations per second, and we can do even more million read operations per second. So it's a few orders of magnitude faster than the existing solutions that we've tested so far, and that's something that is that made us quite proud. Tobias is actually working on making it faster.
Yeah, I'm mainly responsible for the storage engine, and we are doing rounds of benchmarking, and we are now have some numbers that we can communicate. But I'm not. The difficulty with benchmarks is when you do generic benchmarks, you don't know what it means for your concrete application. But in general, we can write up to I have to think we need for 1 million entries from 1 million message instances. So our basic data type, we need between 10 and 20 milliseconds. So on a server. So there is, I do not know any other storage engine that can do that. Of course, there is this is not the whole truth. When you want to insert 1 gigabyte at a time, then the average will slow down. But typically, when you insert 1 million data at once, that's very fast. It's a tens of milliseconds range. then reading is about our goal is 120 million entries per second, and we are now above 100 million per second.
Mm-hmm.
But this is one node, of course.
Okay, thanks. We have 2 more questions at least. Okay, 3 more questions. Okay, so Ishlan, please.
My question is, could you give us examples of who would want to use such a system and what for exactly? So what would be the envisioned industrial applications?
Very sure.
I can give at least 2 examples of projects we're working on. One is for fraud detection in insurance companies, where they receive is a company in Portugal that receives data from all other insurance companies and does the processing, and they have hundreds of rules to process. Say that you get like a day you get 10,000 or 20,000 insurance claims, and you need to apply to each one of them hundreds and hundreds of rules that each one of them requires thousands and thousands of database access. Now these rules on the typical infrastructure that they have right now, these rules take about 30 to 45 minutes to process. So that puts a limit on how many requests they can process a day. Using our application, the same rules and the same amount of data processes in a matter of milliseconds. So with the first test that we did for fraud detection, we went from 45 minutes to 72 milliseconds. Another application that we're developing for a specific client is to monitor energy production. They have thousands and thousands of different sensors installed on each person's house, and those sensors are internet connected, and each day they generate millions of data points that they have to analyze to see if the energy production is within the normal expectation, within the normal curve, or if something went wrong. Again, this is an application that when they first created the first version, they couldn't scale it. They could store between 6 to 8 months of data, and then they have to redo the database again because the application would become ridiculously slow. I mean, for this application to generate between 500 to 700 million data points a year, and they were using a Postgres-based solution, and it just wouldn't scale. With PKNOA, they can scale to billions and billions of data points, and still have queries that will reply in under a millisecond. So these are the applications that we are making, and these are the actual results that we're getting from those applications.
Yeah, in general, perhaps what we are mainly want to target is machine learning, data mining, this kind of stuff. And the problems that we have seen from our customers are interesting in terms of data mining and machine learning, but we have not yet been challenged by really, really big data. So everything, I think I can say that, Wilson, right? So everything that we have seen so far was not that we started to worry about performance.
No, we've never. I mean, we have another application currently running. It's been running for over a year now, and it has over 2 billion data points, and still our queries are quite fast. So we've never actually been challenged in terms of performance. Not yet. I'm sure it will happen sometime soon.
Yeah. There's potential customers say the problem would be related to image processing of terabytes image data, and that would be very interesting because I mean the terabytes as such should not be a problem, but doing image processing on a terabyte, there you have to think about how you do it in terms of algorithms.
Okay, thanks. So next question from Peter.
Yeah, so maybe it's related to the previous question.
So in your first example, in the fraud detection application, so the data there, is it in a relational database, or what is the source of the data? So can you plug in your mechanism onto an existing technology, or do you have to rewrite or transform the data from one place from an existing place into your model? So
the main goal is to, right now we're using a data source. We're using a SQL server as the data source because that's what they're currently using. But the main goal is actually to port all of the data from that data source for them to just use our solution. So because the data source is actually our biggest problem in this project, because just loading that data is quite expensive. But the main idea is to connect the data that comes from the clients, and that data comes via web services, is to connect that data directly to PKNOA and not through a relational database in the middle.
Yeah, okay, that makes sense. But when you mentioned the reduction from 45 minutes to whatever milliseconds, do you calculate the overhead of getting the data from the SQL database?
No. From that, we already, the reduction always already implies that the data is on our side.
Yeah, okay.
It's written in our database, so we're querying our database to then apply the rules. We don't calculate the time that is required to read from SQL Server because, well, that's not really our problem.
But some pre-assumption is that the data, so the source of the data, like you say, must be in an actor data model, basically.
Not necessarily. I mean, we do have some very few basic connectors, although they're not quite hard to implement either way. That we apply queries to the existing data model. We then convert it to whatever model we have on our side, and then we insert it into our database. We call this a accreditation process. It's a process where we define our model, we know of the existing model, we just have to write a piece of software that does the accreditation between the existing traditional model and our model.
Yeah, but if the raw data is fed into a SQL database, for example, then you have to, when the data is new, so it's fresh, then you have to get the data into your representation before you can run any analysis.
Yes, we have to. Being that the end goal is always for the clients to actually convert the actual model as we do and insert data directly into our database.
I think there are two interesting aspects in your question. The first is about the different data models. The other is the relation between the database and its environment from where the data come. And I think at the moment with storing, we are so fast that you have to create an environment that can put stress on the system. But typically, when this is a server that directly receives requests, for example, or inserts from the internet, then you have potentially millions of users that are inserting at the same time. And then the performance we achieve on the storage engine and the distributed system is directly linked to the requests by the environment. When we have an MSSQL server on the other side, there's no stress at all. We are stressed because it takes so long. The other aspect is I think is related to the difference between the models, the data models, and that is very, very interesting. Our first experiences with this was that we looked at the relational data model and we tried to translate it, and that went horribly wrong. Because what we try to do is an
equivalence process.
Yes, it's like object relational
independence.
Exactly. And we ended up with very inefficient and ugly models. And then we decided to change the process and to do this accreditation. Implementation is
Yes, it's a synchronization process.
So you listen to your customers and you understand what their data model is. Then you build your data model, and at the end you make sure that it does the same as the relational database model. But you do not use the relational data model as a blueprint.
Thank you. Okay, so my question would be that you said that when you call a rule, then you get the results when the rule is finished running. So how does this? Well, this sounds a bit synchronous to me. So how do you do that? Do the caller have to wait for the results, or will the result just simply get back as a message that someone else is calling this actor with the result?
For example,
yes, if a rule is calling another rule, then they are synchronous. And if you're calling a large amount of data, then you are calling a large amount of data. It's the responsibility of the programmer to know what's on the other side. And sometimes you can either block, and the rule takes a long time to run, and sometimes you might blow up your memory. There's all of the chance for that to happen. But then again, so does it happen on any kind of database. Now the rules, when we're calling the rules from the triggered option that you have in the first bullet point, those calls are asynchronous because you could be receiving data as a stream, and for each new data point that arrives, we create an asynchronous process. But the rules have to be programmed. When you program a triggered rule, you have to know that they are asynchronous. Does that answer your question? I'm sorry.
Yes.
Okay.
Okay, we have a final question.
Mm-hmm.
And the final question is, I'm somewhat familiar with the problems and technologies used in the geospatial analysis domain, which I think have a lot of similarity to the problems and domains that you target. And their companies tend to use a lot of open source technologies, such as certain Hadoop frameworks such as Spark,
Mm-hmm.
and distributed NoSQL databases, things like this. So how would you compare your technology stack to these technologies?
Okay. There's a few things that in your question that are I'm going to try and break down. The first thing about using the open source, they have some great tools. Spark is an example of a great tool. But the problem that I see there is that you have a Hadoop on the lowest level, then you have Spark, and then you need Zookeeper, and then you need Kafka, and then you need... The problem with creating an open source solution is that theoretically it might sound easy, but they become very complex very quickly. And now it takes a lot just to know how Hadoop works, and it takes a lot just to know how Kafka works. To know how both of them work together, it's almost a recipe for disaster. And these systems, they can very quickly become very complex and very, very hard to maintain and to make changes. We, on the other hand, what we are offering is a single stack, a single tool that does all of these things. So you don't need to go to a different, to Hadoop, to HDFS to do the storage. You don't need to go to Kafka to do the message passing, or some other tool, or like RabbitMQ to do the message passing. No, you have everything integrated in one single tool. And what we also, I think, we do quite better is that because we're a single stack, it's easier to control, and we're faster. We are most definitely faster than all of them built together to create a single solution. That's our main difference. I think the learning curve to start using PKNOA and the investment that you then have in maintenance is actually significantly smaller than using all of these open source tools. And plus, we actually have different concepts. The way we work, the way we treat data, the way we implement the rules is radically different from what they do. we're not going to argue which one is better, because in the end of the day, it's a matter of preference, and you know that's very relative and very subjective. So we're not going to argue preference, but we do things differently. But factually, we are faster. Factually, there's a lot less moving parts. So maintenance or re-implementation or refactoring of rules actually become a lot easier and a lot more straightforward. I hope that answers your question.
Yeah, I think István was nodding, so he accepted your answers. Guys, thanks for the presentations. For me, it was really exciting, and I really hope we will be able to get back to you soon after we, process this inside our here at Inquiry Labs, and then we might be able to go on with some collaboration or cooperation on certain points, especially related to your challenges or open questions.
Yeah, next time we expect some slides from your side solving this challenges.
Ah, okay, cool. That would be a prosperous future together to have something like that. Okay, thank you guys, and have a nice weekend, and talk to you.
Thanks for having us, and thank you all. Okay.
Okay. Bye bye.
Bye bye. Ciao.